Hello everyone and welcome to my YouTube channel. This is my first video and it should be about graph theory. I've never done personally graph theory before, and yeah, I hope you bear with me and I hope I can take you along on that ride about graph theory. Um, this should also be understood as the first of a couple of videos about graph theory, and yeah, let's start. So what is a graph? For that, let me just draw something and then I'll explain. So for example, let's just make some points. Usually we draw points in a diagram as little circles, and then let's just join them somehow, and then we're gonna talk about what the graph is. Like that, maybe just draw it like that to denote the crossing. Yeah, there you go. So this right here, you can see we have 1, 2, 3, 4, 5, 6, 7 points, or as we call them in graph theory, vertices. So we have a vertex set V, and this is consisting of, yeah, I enumerated them, but let's call them A, B, C, D, E, F, G. And G. So we've got a vertex set, and what we also have is edges connecting them. So between A and B we've got the edge E1, and then E2 between B and C, and so on. So E3, E4, E5, E6, E7. Am I right? 1, 2. Oh, I forgot. E8, 3, 4, 5, 6, 7, 8, and then there's a ninth, so I forgot something. E1, 2, 3. Ah, there you go. So this is E9. Okay, and E1 we can denote like that, AB. E2 is BC, and yeah, and so on. And those are called edges. So what is a graph now? A graph is, this right here is a diagram of a graph. This is how we draw graphs. So vertices are points, little circles in the plane, and edges are mostly straight lines, but you can also have curved lines like that. And now, what is a graph? A graph we denote with G, and we can also put a V next to the G just to indicate that it's built out of that certain vertex set here. Yeah, and a graph is built upon a vertex set with those kind of, we call that associations or pairings with indicated by those edges. So it's important to know that a graph is not only the vertex set, but a graph is this family of pairings with in this list here. So a graph has the characteristics of vertices being connected through edges, and we list which vertices are connected how by the list of edges. So I know it's a little bit maybe complicated at first, but we'll see a couple more examples and yeah, what's going on here. We can also say that G is a subset of the product space V cross V. Yeah, the product space for, let's say, for two different V's is just the set of pairings such that A is out of V1 and B is out of V2. And our G could be understood as a subset of, this right here means subset of the product space V cross V. Okay, so this is a graph. A graph is nothing else than a vertex set and the family of pairings upon that vertex set. So what we can have is two kinds of graphs. We can have an undirected graph, as I just have drawn, and we can also have a directed graph. So let's draw a couple of graphs. So maybe this is an undirected graph. We can maybe also connect those two vertices. This is undirected graph, and I don't know, this one is also undirected, but how do we draw directed graphs, or what are directed graphs? So if we have an edge, let's say E from A to B, and let's draw a graph here. This is A, this is B, and we connect it. So this is the edge E. Or let's actually put a capital E here for edges, just to not be confused with the vertices. Yeah, so let's call vertices lowercase with lowercase letters and edges with uppercase letters. So this is E here, and yeah, if this is the same as BA, we say that E is a non-directed edge. And a graph consisting only of undirected edges, we call a non-directed graph. But if this is not the case up here, so let me just maybe take, I don't know, if this up here is not the case, yeah, blue is maybe not the best. Let's take red. If this right here is not the case, so AB is not the same as BA, we say that this edge has a direction, and we point that direction out with an arrowhead here, like this. Okay, so this should be also A, and this is B. Yeah, and BA is just the other way around, like that. Okay. So I started here with an undirected graph, and now I'm going to make it a directed graph, just with putting those little arrowheads on the end of every edge. And if every edge of a graph is directed, we call that a directed graph. So it's pretty straightforward. Okay. So one could ask oneself now, so what about mixed graphs? Does it make sense to have mixed graphs? A mixed graph would be a graph with directed and undirected edges. So let's make sense out of this mixed graph. Does that make sense somehow? And yes, if you think of this example, so let's think of a city map, for example, where we got vertices as street intersections. Let's connect everything here. Yep, like that. And yeah, those vertices are street intersections. Street intersection. And well, now if we put here, let's put here a directed edge, and all the others are undirected. So what could this mean? This could mean that every undirected edge, like so, like here, undirected edge means two-way street, and a directed edge means one-way street. There you go. That's how you make sense of mixed graphs. So a mixed graph is a graph consisting of both directed and undirected graphs. So next I want to talk about isomorphic graphs, and this should be our next definition. Yeah, let's draw two graphs. Let's draw this, I don't know, this graph, and let's draw another one, this graph. So now we ask ourselves, what is the difference between those graphs? Let's denote this one G and this one G prime. And if you look at it, and if you maybe give names to the vertices of the graph, like so, A, B, C, D, you see that really nothing is changing here. If I denote A prime, B prime, C prime, and D prime. So if you remember again, definition of a graph is a set of vertices. So here we've got V, A, B, C, D, and here we got V prime, A prime, B prime, C prime, D prime. So we've got four vertices here, and we've got four vertices here. So this is very similar, and a graph also has the characteristic of those family of pairings. And here I've got E1, E2, E3, E4, So E1 is AB, E2 is BC, E3 is CD, and then we have E4 DA. Or as it's undirected, we can also call it AD. And here on the right side with G prime, we got A1, E1, sorry, prime, E2 prime, E3 prime, E4 prime. There you go. And this is A prime, B prime. E2 is B prime, C prime. E3 is C prime, D prime. And E4 is A prime, D prime. And if we observe correctly now, we see that, yeah, what we see that graph G has 4 vertices, graph G has 4 vertices, as has graph G prime, and in graph G we have those 4 relations here, those 4 pairings, but we see that G prime has the same relations. So this leads to the following definition: two graphs G and G prime shall be called isomorphic when there is a one-to-one correspondence between their vertex sets V and V prime, such that the corresponding vertices are joined by edges in one of them only if they are also joined in the other. So and also this is for the undirected graph, but for directed graphs, if the edges are directed, their directions must also correspond. So we see here in this example, we have a one-to-one relation here. A goes to A prime, B goes to B prime, C goes to C prime, D goes to D prime. This is a one-to-one relation between those vertex sets. And this edge here, or these two vertices, are connected here and here also. So we have a one-to-one correspondence between the vertex sets and the family of associations or pairings. So this is then we call a graph isomorphic. We will see later on a exercise about that. So let's move forward. We have a couple of definitions still left to discuss. So an isolated vertex. So an isolated vertex is nothing else than, let's say, if we have this graph here, we have vertex A, B, and C. C is an isolated vertex because it is not incident to any edge. Oh yeah, forgot to say what incident means. So in an edge A, B, we say E is incident to A and B, and vice versa, we say A and B are incident to E. Okay, so this is the definition of incident, and an isolated vertex is just a vertex which is not incident to any edge. So it's like I have drawn here, just an edge which is isolated. So this is an isolated vertex, and if we have a graph consisting only of isolated vertices like that, like so, we call that a null graph. This is the null graph, and we denote it as G equals 0. Or here we have a prime, but let's take that away. There you go. So a null graph is just a graph consisting of isolated vertices. Now let's take a look at a complete graph. A complete graph so we can maybe say this is a definition, this is a definition, this is a definition. And now we come to the complete graph. We denote it as U or UV, and this is a graph whose edges are all pairs of possible associations for two different vertices. So the edges are, the set of edges are as follows: A, B in our product set V, V, such that A is not equal to B. So we don't allow the starting point to be the end point. So it is a graph whose edges are all pairs of possible associations for two different, and this means different, vertices A and B and V. So for example, this one is a complete graph with 4 vertices, and this one is a complete graph for 5 vertices. So I just have to make sure that every vertex is connected. So 2 different vertices are connected, so like so, so, and I think this should be it. Yeah, that's it. So this is a complete graph. Now, again, a couple of definitions. A converse graph. Converse graph. This makes only sense if we have a couple of, or at least one directed edge. So let's explain it with a drawing. I have one directed edge, or let's say every edge is directed, and this is G, and I denote by G star, I denote the converse graph. And how do I get the converse graph? Well, guess what? I just flip the directions. So if I maybe had, let's say I had a mixed graph with this edge being undirected, so I just flip the directions of every edge, every directed edge. That's a converse graph. Then we have an associated undirected graph. So what is that? An associated undirected graph is just, well, if I take my little picture up here, there you go. I'll explain it again with the picture. Yeah, and we denote by GU. This little U is for undirected. So this is the associated graph, but we just take every directed edge to be an undirected. So we omit directions in all directed edges, and this is the undirected graph right here on the right side, on the right hand side. And then we have also the process of duplication. So what is the process of duplication? Well, this is if I have this graph right here, I can get GD, D for duplication. Well, this is also easy explained by a drawing, by a diagram. I take every undirected edge and duplicate it, and I put all possible, so the 2 possible directions instead of the undirected edge. So this right here is the process what I'm doing is the process of duplication. So as you have seen now, a converse graph is just, so if we talk about G here being undirected, then G star is also undirected. If G is mixed or directed, then G star is also again mixed or directed. So we just flip the direction of the directed edges. But an undirected graph is going to be still an undirected graph, and the directed graph is still going to be a directed graph, and mixed is going to be mixed. Associated undirected graph, what this does is it produces undirected graphs. So we will have undirected, directed, or mixed graphs, which then become undirected. Okay. And process of duplication is, yeah, one could say the other way around. We have undirected graphs. I'm not sure if we can have directed graphs and then duplicate them. Let's say if this right here was a directed edge. Yeah, I guess this could work. Or we can have undirected, directed, or mixed graphs, and then it for sure you produce a directed graph. Okay, so just wanted to point that out. There you go. Yeah, and here was an example of process of duplication. So sometimes we want maybe to enlarge a graph concept a little bit. We haven't talked about loops, so this is going to be our first enlargement of the concept of graphs. So we will allow for loops, and this is nothing else than the start point and the end point of an edge being the same vertex. And here is an edge and a loop we draw like this. Okay. Well, and then we can enlarge our complete graph U to a complete graph with loops U 0. We denote that little index 0 for having a loop. So for example, previously we had this here, complete graph with V equals 4. So this is a notation for the count of elements of a set here. And then we just like that put a loop on every edge, and then we receive U0. Okay. Yeah. So if you think of, where was it? Here. I will take that. If you think of the set of edges of a directed graph with E0, we just say we don't restrict ourselves to a not equal to B. We just take really every possible pairing of our product space V cross V. Yeah, that would be the first enlargement of the concept, and the second enlargement, this is, let's say, the first enlargement, and then we go to the second enlargement. And the second enlargement is going to be to allow for several distinct edges. Several distinct edges. So what this means, I can have, in a non-directed graph, I can have So let's just like that. A, B. I can have this, this, maybe again, one and again. So I can have a couple of edges between two vertices, and they shall be seen as really distinct edges. And in an directed graph, I can also have this, but like that. So if I have AB, and let's say I have E1, E2 in direction A to B, and I have E3, E4 in direction B from B to A. So I can have several directed graphs. And why does this make sense? So, for example, yeah, think of, I don't know, if we look at this right here, this graph right here. So think of maybe the records of any sports league you like. And let's say A is a team and B is a team. And yeah, this is a possible pairing in your sports league. And now A and B, they play a game, and if they play, we connect them with an edge. And if A wins over B, we could say that this edge is directed towards B. And then they play maybe a second time in the season, and A wins again, and then they play a third time where B wins over A this time, and the fourth time where again B wins over A. And if maybe it is possible to play a tie game, we could say we can have a mixed graph and then an undirected edge. An undirected edge means tie game. Okay, so there such an enlargement of our graph concept could make sense, to have several distinct edges. Yeah, okay, so let's move on. I have one definition left, and then we're gonna do a couple of exercises, and that's it for this video. So, planar. What is planar? A graph is called planar if it can be drawn in the plane in such a manner that all intersections of edges in the diagram are vertices of G. So, for example, this right here. This is a planar graph, but um, I don't know, this right here is not a planar graph. And well, no, this is a planar graph because you can take those two edges away and connect them differently, like so and like so, and then we have a planar graph. But I wanted to draw a non-planar graph, so this right here is planar and non-planar. So how do we omit? How do we draw a graph where we cannot make it planar again? So let's have this cross here and connect those two vertices. So here you see we have this, this, this. We have restricted ourselves. We made an inner area here with a cross of two edges, but this is not a vertex, and we have no chance of connecting those four edges to make it planar, to omit this crossing here. Yeah, and that's planar. And there we're gonna see also an exercise. So now let's do two exercises. So exercise 1. Exercise 1. I will have to draw a little because we have to show that the two graphs I'm gonna draw now are isomorphic. So 1, 2, 3, 4, 5, 6, 7. Gonna connect them like so. And because I want to have a similar one, I'm gonna copy it real quick, put it here, and yeah. So the one I'm gonna connect like so. There you go. And the other one I'm gonna connect like that. And then like this, like this. Yeah, I'm done. There you go. So I have a graph, let's call it G and G prime. And now, I'm sure you can maybe see that they are isomorphic, but what does isomorphic mean again? Isomorphic means that we have a one-to-one correspondence between those vertex sets. So we see here we have 7 vertices, and we also have 7 vertices. So we can easily somehow put a one-to-one correspondence between those sets, but we have to respect the side constraint, or the constraint which makes the definition of being isomorphic, namely that two vertices are connected in G if and only if their corresponding vertices in G prime are also connected. So how we solve that exercise is going to be that we are going to name those vertices in a certain way, such that the definition is fulfilled. So just bear with me, and I'm gonna start right now. So let's call this vertex here A, and then we see that, or let's just call every vertex set here A, B, C, D, E, F, and G. So start from the point of view of A. So A is connected to B, G, D, and E. Yeah, right. No, B, G, C, and F. Sorry, my bad. But it is not connected to D and E. If you look here, it is not connected to D and E. And this is a good information. So let's take this away just to not get confused. So if I now call this uppermost vertex A prime, so here we see A prime is connected to this vertex, to this vertex, to this here, and this here. So we know, since in G A is not connected to D and E, that this vertex here, this is not a connection, so I'm gonna take it away again, but this right here has to be D prime, or maybe E prime. and this right here is no connection here, so this has to be d prime or e prime. I'm gonna take a guess and put d and e prime like so. So again, just the explanation why d prime is that and e prime is that. In G, A is not connected to D and E, so it must not be connected. A prime must not be connected to D prime and E prime in G prime. So therefore, this right here has to be D prime or E prime, and this right here has to be E prime or D prime. Okay, now we put ourselves into the point of view of D prime, or let's go here to D right now, and we see that D is not connected to A and G. A and G. Well, as we started previously from A prime, so D prime is not connected to A prime, but it must not be connected to G prime as well, since D is not connected to G. So where is the other? Here it is. There is no connection, so this right here has to be G prime. Okay, and same argument works with E. If I put myself here into E, it is not connected to A and B, so it must not be connected to A prime. E prime must not be connected to A prime, and this one is B prime. Okay, and now all we have left is those two edges. So how should we call them? Now if we put ourselves here into B prime, the corresponding vertex is B here. So B is connected to D prime, so D here, yes. G prime, so B, G here. And A prime, so this is A here. And what we also have is the connection to C. So this one should be C prime. Okay, and the same works with the point of view of G prime. G prime is connected to A prime, to E prime and B prime, and G is connected to A, B, and E, but it is also connected to F, so this one is F prime. And through construction, we have, in every step, we have respected that two vertices in G here are connected if and only if they are connected here in G prime by construction. Again, you can go ahead, pause the video maybe and check for yourselves, then that really every two vertices in G are connected if and only if they are connected in G prime. Okay, so let's go to the next exercise, exercise 2. And this is going to be the exercise about the three houses and three wells. So we have the following situation. We have three bad neighbors and they have three wells for common use. And now the question is, let me just draw the three bad neighbors like so. House 1, house 2, house 3, and those are a little big vertices. And we have three wells for common use. W1, sorry, this should be a 2, and W3. A little big vertices, but let's stick with it. And now the question is, can we construct separate non-intersecting paths from each house to each of the wells? So I'm going to naively just draw something. So from each house to each well. So start from house 1 to well 1, well 2, well 3. Then from house 2, well 1, well 2, well 3. You see it is intersecting a lot, like here, here, here. And from house 3 to well 1, well 2, well 3. So the question is, can we draw a non-intersecting, can we construct separate non-intersecting paths from each house to each of the wells? I just did it with intersecting paths, but can this be made with non-intersecting paths? So if you remember our definition about planar, this just means, can we make this graph right here planar? Because the definition of planar is that really every intersection of two paths or two edges is also a vertex. But here, as I have drawn, it clearly is not. There are a lot of intersections which are not vertices in our vertex set. So yeah, and by the way, if you Google this, you will see that we can also arrange it like that. And well 1, well 2, well 3. So can we from H1 draw this, 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 from H2 connect to every well, like so, and from H3 connect to this, this, this. So can we, those are two same graphs, so this is G and this is G, or in the world outside we have a special name for this, K33, and this is also K33. These two diagrams represent the same graph, also called Thomson graph. Thomson graph. And the question is, can we make that graph planar? So can we construct separate non-intersecting paths from each house to each well? And the answer is going to be no, but why? So what we're going to do, we're going to show that by contradiction. So let's put, for example, the three wells here in the middle. Let's make a little, yeah, like that. And the house here and the house here. And we connect the first house to the three wells, the second house to the three wells. And now, where can I put the third house to connect it to the three wells without crossing any of the paths or edges here? So what we see is we have three areas here. We have this area right here. This is an area here. Then we have this area here. And we have everything outside. Okay. So we have three possible areas to put our house 3. So let's start maybe we put it here, somewhere here, house 3. And now we can connect it without intersecting any other path with well 1 easily, with well 2 easily, but we cannot connect it with well 3 without crossing any of the paths, because we are in this area. Yeah, we are kind of trapped in this area up here. So we are trapped here, and there is no path to the well 3 without crossing, namely here. Yeah, without crossing any of the paths, because we are trapped in this area up here. Same argument goes with the lower area. If we put H3 somewhere here, we can connect it easily with W2, well 2 and well 3. There you go. We haven't crossed any path, but we cannot connect it to well 1, because again, we are trapped in this area, this lower area here. Okay, and same argument works for our third area we have to check. So if you put it somewhere here, is 3, we can easily connect it to well 3. We can easily connect it to well 1 without crossing any path, but we cannot reach well 2 here without crossing any of the paths, because well 2 is trapped in this area here. So we have ourselves a contradiction. That's why this is a no. So the answer is no, one cannot construct separate non-intersecting paths from each house to each of the wells. So that's it. Thank you for watching this video, and I hope to see you again for my next video. And I hope you had fun with me and this video, and leave a comment if you have any suggestions about, I don't know, since this is really my first video about the quality of I don't know, the sound, the quality of the pictures, the quality of my handwriting, although I don't know if I can change anything to it. And yeah, I'll be happy to hear from you in the comments what was good, what was not so good, and see you next time. Thanks for watching. Bye.